Particle size distribution or grain size distribution. Particle size distribution is a very common tool in earth science, geology, geography, any other sedimentology science. Anybody who studies the landforms, earth, the environment around us, they know about particle size distribution. What is it? Let's figure out why it's so important, what it can tell us about the landscape around us, its history, a region, or a condition, specific condition when this landform was formed. So particle size or grain size is the diameter of individual grains of the sediment. So when we study particle size distribution, we're looking at specific size of each grain in whatever material you have in the sediment. So it could be your sand on the beach, or it could be something in the riverbed. You can just look in your garden, whatever material you're working with, you want to know what the grain size distribution. It also could be lithified particles in the clastic rocks. And what does it mean, lithified? So it's mean that you have a piece of rock which already solid right now, but in the past it was sand or something like that been created from bringing together different particles or crushing something, creating different smaller particles, and then with time or under the pressure they lithified or become solid rock. So called clastic rocks because they're composed originally from clasts or grains. They've been brought together from different environments, maybe not different, but they've been broken first and then they've been lithified again. And it also could be applied to other granular materials, so it could be something in industry, it could be your glass beads created, you talk about the grain size distribution of it, or some artificially produced material or sand for your quarry or something like that, so something what you use in the industry. The main things you have to remember about grain size distributions. So first of all, there's very important characteristics of clastic sedimentary rock. So rocks that are created from other rocks, we call them clastic, and sedimentary, it's mean they've been broken before and brought together. So they could be coming from different environments, or it's all same environment, just broken apart rocks. This kind of stuff. So if you're in the mountains and you see some rocks lying down next to the slope, so it's rockfall material, the rocks that fall down from that slope, but the grain by grain. It could be a little landslide, so when you have a piece of mountain falling down, it's crushed it on a way, but it's gonna stay more or less intact in the same deposit place. It could be material that come from whole catchment of big river, for example, Amazon River. It's brought the material from all around, like half of the South America, and it's all end up in the beach that they brought towards the Atlantic Ocean. So this material, they've been together in one place, found around the beach of the Atlantic Ocean, in the mouth of the Amazon River, before come from all different places, mountains or plains of South America. Amazon River, the basement. So keep it in mind. And it's also fundamental because it's give you understanding of, for example, how those rocks been created, how they've been broken, what kind of energy created those rocks. It was created grain by grain, or it was created one catastrophic event, everything collapsed and crushed. So different things it can tell you about it. It's also tell you about how long and how it's been transported, for example, by wind or the water, or like a mud flow, or by people, for example. It also can tell you how rounded it is, so it's how long it's been exposed to water or crushing, mixing with other rocks. So it's become more or less angular, more rounded, and it can tell you maybe how far it's been traveled or how long it been is this broken piece. If you go to the mountains and see freshly broken rocks, they're very sharp, irrespectively of the lithology. But at the same time, if you go on the beach and you see those sand, they've been spinning more years every day, rolling, forcing back by the wave action. It could tell you that these rocks been there a long time, they've been sorted well, and they're more or less same grain size distribution, nicely sorted on the beach, and they're very rounded, some of them. So it reflects weathering and erosional history, that's what we talked, and provides idea about the transportation mode. That's exactly what I'm saying. Is it traveling through the mountains, far away by the river or by the glacier, or is it being deposited straight away next to the slope? It didn't travel much, or it's being blown by the wind kilometers away from its source. It can tell you that too. Another thing you have to remember, very important, that most of the rocks, grains in your material are non-spherical, so they will be in peculiar form, shape, from breaking or grounding or something else. It's not perfect sphere or cube or something being broken off. But in our estimation and description of grain size distribution, for example, we calculated it using a laser particle size analysis, we put in estimation that it's in particular size, particular shape. You have to keep it in mind. So we use this term of nominal diameter, or of the grain, is the diameter of the sphere that has equal volume as that of the grain. So this is something very mathematically approximation. So when you look on the scale, and on the right you can see there's grades and classes of the grains. You can probably heard about sand, silts, clays, and so on. So it depends on each size, we put them in these boxes. So for example, we have here in millimeters, boulders more than 256 millimeters, everything bigger will be boulders, and then less will be cobble, pebble and granites till 2 millimeters, so everything from 2 till 64 millimeters will be this granite, pebble, cobbles or gravels. And then finer we go to the sand from 2 millimeters till 63 micron, or 0.061 millimeters. So this is the 63 micron, 1 micron, it's the 1,000th of your millimeter. So trying to imagine this. And we have sand, so we have different gradations, very fine, medium, coarse, very coarse sand, from 1 till 2 mil coarse sand, till half mil very coarse sand, till half mil coarse, then medium, till quarter of the millimeter. And then you go to this finer and very fine sand, still sand. And then you go to the silts then. Silts, everything fine, and then 63 micron till 4 micron. You can imagine it's very fine. And everything fine is clays. And here we're not talking about clays as the chemically reactive type of like soil clays. Some people confuse this. But clay also uses a chemical term for particular particles that have particular geochemistry and they react with the environment. Here we're talking about actual size. So no matter what you take and you crushed it till the size that it's less than 4 micron in size, one of the longest axes of this, whatever shape it is, grain will be less than 4 micron, it will be your clays. And here it doesn't matter which type of lithology or chemistry of this particle. So that's your grain size distribution, which you can find in the world. And more or less, people kind of agree that they of this particular size. So sometimes scales a little bit different. For example, I used to work with sand silt started from 63 micron, here 61, but it's plus minus, it's more or less same. Depends on the scale you use, the country, on standards. Also depends on what type of science branch you're working with. So if you're working something geochemistry, maybe something different. If it's soils for agriculture, there'll be a different gradation, maybe slightly. But in general, sand, silts, clays, more or less everybody talk about same sizes. But keep in mind this estimation, this simplification into the terms and how we measure it. Because you can imagine we do not measure each grain size and then we recorded it and created this graph of grain size distribution. We estimating the grain size distribution by sieving it. So through the sieves, longer but very thin type of particle can go through smaller mesh. Depends which axis will kind of go through the hole. So you might have this plus minus mistakes when you measure it anyway. And then very fine stuff like silts and clays, very hard to see, for example, because they kind of tend to stick together. So we had to use different techniques. For example, settle material in the water and see by the speed of settling velocity, you can calculate your grain size distribution, or by using laser sizer diffraction methods. It's when you put your material, everything usually is smaller than sands, you put it in water and you put it into this chamber and laser beam going through this chamber and give you, from the light that diffracted from the particles, give you estimation of your grain size distribution. So remember, there's always approximation of your grain size distribution. in reality, you cannot measure each grain. And here you can see we use the two main methods. Udden-Wentworth scale, that's the standard one. The main idea that you can see there's kind of like some kind of regression here. So the scale divides consecutive classes of the grain size in millimeter scale by multipliers of 2 on the higher side and decrease by multiplier of half on the lower side. So if we start from 1 millimeter, it's usually from coarse sand till 2 millimeter, and then you multiply by 2 will be 4, and then will be 64. So you go into the logarithmic progression here. Phi crumb-vein scale, using the same sizes, same terminology, but here just a little bit simplified. So just by the doubling of the diameter of a grain in millimeter, making it on a logarithmic scale. Depends where you are, you can see both these names. Millimeter are usually on the mesh, they indicate both. I've always been using the millimeter scale, but also I kind of tend to think about grain size distribution if I find things in micron scale. So if everything finer than the silts, I'm thinking about microns. And that's how it's represented more or less. So on the graph, you can have this grains, which that's just approximation how it's gonna look like in reality. But you also have this rounding situation, so it's a rounded or sorting, poorly sorted, well sorted. So there's different things you can use also to describe the material. But the grain size will be something basic, so you need to know what sizes you're talking about before you start describing other properties. And you can more or less describe it in the field, kind of fast description. There are some methods you can use in the field, but usually we take material home and we sieve it, or we can sieve it in the field, and we're trying to figure out what the grain size distribution for this particular deposit of material. And let's just come back for a moment to understand the sizes, and I know that it's quite hard to put the concept of the size in your mind. So here we just have a look at meter scales, and we're gonna work with the metric system. So the first one will be 1 meter. 1 meter is the 1 meter. That's what we usually work with the 1 meter. And then if you multiply it by 1,000, so 1,000 meters, you're 1 kilometer. So kilometer is quite maybe if you're driving your car, it's kind of, you understand what I'm talking about, 1 kilometer. When I was a child and my father always described me, I had to understood how much kilometers, how far, and in the car I was always curious about these things, especially when you're driving and you see 5 kilometers till this village or 10 kilometers till that village. And my father was always telling me, if you count till 60, approximately 1 minute, there will be your 1 kilometer. So I was always checking this and still do sometime when I'm driving. But these days, usually if you're driving 60 kilometers an hour, it's easy, but if you're 100, so it'll be a little bit faster, so you can play with that. But you kind of have an idea what is a 1 kilometer, what is a 1 meter. Then we go megameters, so it's 1 million of the meters. So 1,000 of kilometers, it's megameter, and gigameter, it's 1 billion of the meters. That's something harder to understand. And then let's look on the finer stuff. So that's what we work with. So 1 meter, not hard to understand. And then you go 1/10 of your 1 meter, it's decimeter. 100 of 1 meter is centimeter. And everybody kind of work with centimeters. Everybody understand what is a centimeter. There's the things you can look on your fingers, for example, and kind of knowing the diameter of your finger. No, more or less, this is 1 millimeter or 1 centimeter, 1.2. Next thing we're talking about is the millimeters. It's 1,000 of meter. And remember, thousands of meters is kilometer, but 1,000 of meter is the millimeter. And it's a very small thing. Then we go to the micrometers. And as I told you, it's 1,000 of millimeter or 1 million of meter. That's why we call it micrometer. And then we're going to the nanometer realm, and it's very hard to understand nanometers, but it's sub-micron size. 1 nanometer, it's 1 billion of meter. Let's have a look for some examples. So here you can see the diameter of a human hair, 1 human hair. You can kind of, if you take it, you can see it nicely, depends on your vision. And this is from 20 to 40 micron. So this already sub-millimeter size we're talking about. So 40 micron, remember, what is it? 1 micron, it's 1,000. So 40 micron, it's quite small, yeah? Then we're looking on human red blood cells, and they're from 5 till 10 micron, and that's, for me, it's a little bit surprisingly large. So you basically 1/4 or half of your hair will be your blood cell. That's pretty big. Then we're going to the spiderweb silk thread. That's, you commonly see it. Sometimes you can't even see it, but you can feel it. We're talking about 2-3 microns, so that's the size approximately. We're talking about the one thread will be from 2 to 3 micron. Bacteria will be 1 micron size, quite small. And the viruses, it's sub-micron, it's nanometers. You're talking about 30-50 nanometers. And when you're talking about viruses, remember about how viruses spread and how we protect ourselves from the viruses. And then look at the size. So how fine the barrier has to be to stop the viruses to spread. That's the question for you. But this just gives you an idea about the sizes. You can see that the rocks could be as big as the boulders, bigger than us. A very large grain size distribution. Here the boulder just sitting in deposit, and obviously half of it sitting under the ground. The grains could be very fine. So this is the under microscope, the sand grains, the ones you can find in a river, on a beach, for example. The rounded particles, they actually have a different color, as it gives us a little bit different colors of the sand. That's another photograph of the sand, more or less all kind of silica here. You can see some other lithologies, and that's the scale 1 millimeter for you. You can actually see this. Simple lens, hand lens or microscope can show you this. Next time you're on the beach, observe. And that's the same grains, but under scanning electron microscope. So a little bit zoom image can give you better resolution. You can see there's 100 micron, the scale bar. So all of these ones kind of like half mil or so. Nice edges. You can see some were rounded, some are broken. You can see a little bit of lithology. And then if you look on grains under the scanning microscope, even finer, you can see intricate features on it. There's just a silica, probably sand grain, 10 micron in diameter. There's another particles, and there's a carbonated sand or silica sand. Sand silicates mean quartz. See how different they are actually. And carbonated, you can see how it's these pores, it's the weathering, erosion happening, chemical erosion in the surface. And this is the volcanic grain. And here we already see the clays. They are finer and they already chemically behave a little bit different, and they are interesting to talk about. So that's just examples of the grains, and let's in next video talk about how we measure and created grain size distribution and why.